This is tutorial 26. Today we will start the last chapter in fluid mechanics, that is chapter 9 about external flow. In particular, today we will talk a lot about drag. By external flow, we are dealing with a flow over an immersed body. For example, air flows over an airplane as it flies across the sky. We are interested in the force acting on an immersed body, since we want so many things around us to move effectively in a fluid. For a golf ball, we want to hit a long range. For cars and planes, we want to save the fuel. And there are so many other examples. A general flow is three-dimensional, but the problem is quite complex, so that people use computational fluid dynamics to deal with that. But some object is sufficiently long so that the end effect can be neglected. That is, we can take the flow as two-dimensional. In addition, some objects are isosymmetric. That is, the object can be obtained by revolving a section 360 degrees. And that gives another type of simplification. Also, in this chapter, we assume that the free stream velocity is uniform and steady. Although this assumption is not true for an airplane, this assumption offers a great simplification. By the assumption, we can now conveniently define the flow direction as the x direction and the normal direction as y. The drag force is just the x component of the equivalent force acting on the body, and the lift is just the y component. As shown in the figure, the fluid force acting on the body is due to both the pressure and the shear stress, so that we can write an expression for the two components like this. For drag force, people usually call this term due to the pressure as pressure drag, and this term as the friction drag. But then, sometimes we don't have so much detail about the pressure and the shear stress, so we again use the empirical relations. The two fluid force components are compared to the stagnation pressure as if the flow is frictionless. To see this, we apply Bernoulli equation between a point far away from the surface and a point on the surface. If the gravitational effect is negligible, we can write so point 2 is of course the stagnation point, so this term goes away, and if the free stream pressure is atmospheric, it is now clear to us that the stagnation pressure is in the denominator here. To get a dimensionless number, we multiply the stagnation pressure by the so-called characteristic area. Such area can be one of these areas, and that depends on the physics of the flow. The frontal area is obtained by projecting the object onto the yz plane, so that if you look the object this way, you will see a rectangle with D and L. And similarly, the planeform area is obtained by projecting the object onto the xz plane. So, now let's do our first example. It is just a plate. Only the top and the bottom is subjected to the pressure and the shear stress. The end effects are neglected. If we label the top surface as 1 and the bottom surface as 2, we can break this integral as but then, the theta is the angle that the normal vector makes with the x-axis. So, for surface 1, this is the normal vector. If this is 7 degrees, then theta is 83 degrees. And for surface 2, and this is 7 degrees, so that this angle is. But before we continue, I want to talk about the sign convention for the shear stress first. The sign convention is that for the top surface, this side is positive, and for the bottom surface, this direction is the positive. But then, for the shear stress now, the shear stress is going like this in both the top and the bottom surface. So the bottom side shall be taken as negative. So that we can now plug the values in. And for the bottom surface, and finally we have to multiply by the area. So we compute this long chain of numbers. But I don't like this method since we have to always look at the signs. Now I show another way to do this problem. First, we set another coordinate system, and we draw the stresses acting on the plate. And we calculate the forces acting on the U and V directions, that is, parallel to the plate and normal to the plate. The area is 1. We look at our plate again. Now we have these two forces. We want to find the X component of force acting on the plate and the total Y components of force acting on the plate. We do this by decomposing the forces, Fu and Fe. And this is 7 degrees, so that we can obtain expressions for the drag force and the lift in terms of Fu and Fe. Or we can write this as and with theta equals 7 degrees, and we have found Fu and Fe already, we can calculate this as. Note that this matrix here is not the rotational matrix with 7 degrees counterclockwise. This is the inverse of the ordinary rotational matrix. We have to use the inverse. It is because we are not applying rotation on the vector itself. We are just applying a counterclockwise rotation on the basis vectors. This kind of transformation is called the passive transformation. It is just like if you have 1000 grams. If you want to express the same quantity by scaling the units by 1000, that is, expressing 1000 grams in terms of kilogram, then we have to scale down the value by 1000, and these quantities shall be the same. The resultant of Fu and Fe shall be the same as the resultant of Fl and Fd. If you recall that the uniform flow involving incompressible fluid is indeed potential flow. For potential flow, and if we further assume that the flow is inviscid, then we can apply the Bernoulli equation. Since the shear contribution has gone away, the drag force is simply contributed by the pressure force, and it can be written this way. And people develop this expression for finding the drag and the lift force under potential flow. As you recall, the potential functions are just linear functions in x and y. So, for a uniform flow, this term is just a constant. And if you integrate a constant over a closed contour, the whole integral becomes 0. So both the drag and the lift are just 0. And we have arrived at this conclusion. There is no drag and lift force for all shapes under the potential theory with the inviscid assumption. Well, I just put this formula here for your interest, so don't be so serious about that. You just have to know that using the potential theory under the inviscid assumption will give ridiculous answers. This result given by the potential theory is of course ridiculous, since if you stand in the wind, you can certainly feel the drag force acting on you. And if we study the drag force acting on a smooth sphere by varying the Reynolds number, we find that the drag force is a strange function of Reynolds number. and the drag coefficient, not the drag force, is given in this chart. To carefully study this relation, we label points 1, 2, 3, 4, 5, and look at what happens for the flow over the sphere at each point. At point 1, that is, the Reynolds number is really small, much smaller than 1, then we call this flow as creeping flow, Stokes flow, or laminar flow. And the drag force is just given by this simple expression. A is in fact the radius. For this kind of low Reynolds number flow, the drag contributed by the pressure and the shear is 1.2. That is, shear is more important. It is because the fixed gas effect is really important in such flows. And from the Stokes law, we can show that the drag coefficient is given by 24 divided by the Reynolds number. The drag coefficient is defined as the drag force divided by the stagnation pressure times the area. And here the area for a sphere is frontal area, and that is pi r squared. This cancels out, and the radius becomes diameter divided by 2. So this is 24 divided by Reynolds number. In fact, we can show that the Stokes law is true by using the Navier-Stokes equation. Since the Reynolds number is really small, and the Reynolds number is defined as the inertial force divided by the fixed gas force, so that we can neglect this term completely, and what's left is to solve this second-order linear partial differential equation. And in spherical coordinates, we can write this equation as these two guys, and the continuity equation is given by this. So that after solving for the velocity, we can compute the drag. And it is really true that pressure to fixed gas effect is 1 to 2. And the drag force is exactly the same as the one given by the Stokes law. We call that for the Stokes flow, the fixed gas effect is important throughout the flow. However, if we further increase the Reynolds number to this range, that is, about this range, there are some regions in front of the sphere that the fixed gas effect is not as important. And in the shaded gray region, the fixed gas effect is still important. But then, we see a new interesting phenomenon here. From this streamline, this particle would fly off from the surface and goes this way. And the particle in this region is moving in a vortex. We call that this bubble as the separation bubble, and this phenomenon as flow separation. So, why this would occur? If we look at a car moving up a ramp, if its velocity is high enough, the friction is not enough to hold the tires onto the road. Then the car will fly off from the ramp and detach from the road surface. So, you can imagine that the particles above this point will always go above the separation bubble. And in fact, inside the separation bubble is nearly empty. This creates a pressure lower than the atmospheric pressure. In front of the sphere, the pressure is higher than the atmospheric pressure. In particular, when we look at this point is the stagnation pressure. So, this pressure difference will create a pressure drag in this direction. And unlike in Stokes flow, which the friction drag is higher than the pressure drag, in this case, the pressure drag is higher than the friction drag. But still, the friction drag is not negligible since there is still a large region that the fixed gas effect is important. Now, further increase the Reynolds number, and this separation bubble will break down and form a vortex street. For this vortex street, the two broken separation bubbles will find space for itself, so that sometimes this guy wins and sometimes this guy wins and so on. So you can see this flow pattern of vortex street. And if you have looked at the simulation in class, you see that this road sign will be oscillating. If you have not studied fluid mechanics, then you may think that the wind direction is always changing. But in fact, the flow direction is always in one direction, and it is the two competing vortices make the road sign oscillate. By the way, the term wake here means that the pressure in this region is particularly low due to the flow separation. And if we further increase the Reynolds number to 0.4 here, then we see another phenomenon, that is, the formation of a thin boundary layer. In this thin boundary layer, the flow is laminar, and this boundary layer is really thin compared to the diameter. Also, if you still remember in the previous two slides, the separation bubble is originally here. And this point is where the flow separation starts. And if we further increase the Reynolds number in this region, this separation point would move backward to its limiting position. And the wake region where the pressure is low will be increased. And there is much more contribution from the pressure, so that the frictional drag is already negligible compared to the pressure drag. And we say that the drag is now pressure dominated. And in this region, the flow physics remains nearly the same, so that the drag coefficient is now a constant. But the drag force is in fact increased, since the drag force is proportional to the velocity squared. So what is a boundary layer? Boundary layers are the regions where the viscous effect cannot be negated. In these regions, the streamlines are somehow distorted. And for a flow over a plate, people develop expressions for laminar boundary layer. And this is the famous solution offered by this guy. You shall visit the concept of boundary layer again in heat transfer. But looking at this pair of equations, if we fix a location in the plate, then the boundary layer is inversely proportional to the square root of the Reynolds number. And the Reynolds number is given by. So, since x is fixed, the boundary layer fixedness is proportional to this guy. If we fix the velocity and move the x, we get, and that is proportional to the square root of x. In this figure, you see that is about the shape of the square root x. And if we further increase the Reynolds number, we see that there is a sudden drop in this point, and there are a few applications using this fact. In this point, the boundary layer suddenly becomes turbulent. In turbulent flow, the momentum transfer is really effective, and so that there are more particles stuck to the surface of the sphere, and the separation points move forward like this. The area of the wake region is smaller, and the pressure drag is decreased significantly. As a consequence, both the drag and the drag coefficient decrease. And not only for sphere, for plate, there are also similar laminar to turbulent boundary layer transitions. So, we have finished talking about the effect of Reynolds number on a flow over a sphere. In general, the drag coefficient is a function of several quantities. And in this course, we are doing these three: the shape, the Reynolds number, and the surface roughness or relative roughness. We have already finished talking about the effect of Reynolds number. And let's first talk about the effect of shape. To consider the drag, the shape is really an important consideration. And the size of the object is not really as important as the shape. In the figure here, can you believe that the drag produced by this guy is same as the drag produced by this guy? But that is really the case. It is because the geometry of this guy blocks the flow. Shapes like sphere and cylinder are considered as flow-blocking bodies, and we have another term that is blunt bodies. To calculate their drags, we usually use the frontal area. For streamlined bodies like horizontal plates and airfoil, we usually use the plane form area, and the drag for the streamlined body is much lower. In car and airplane designing, we usually like the streamlined bodies over blunt bodies. It is because we want to reduce the fuel consumption. If the drag is large, then we have to use much more fuel to overcome the resistance force. In the previous slides, we have talked about flow over a smooth sphere. And in fact, the book used the flow over a smooth cylinder, and that is exactly the same as the flow over a sphere. The only difference is that the values are a little bit different. We finally close our discussion about drag by looking at the effect of surface roughness. You may wonder why we add this small piece on the golf ball. This is rather counterintuitive. If we want to reduce the resistance force of an object over a flow, then we want it to be as smooth as possible. So why shall we make the surface of the golf ball to be rough? The answer lies in this graph. We want to have this point when the boundary layer becomes turbulent. It is because both the drag and the drag coefficient decrease at this point. So let's find out what is the velocity required for producing such a Reynolds number, 5 times 10 to the power 5. So let's find the velocity required to produce this Reynolds number. And if we solve for u, we find that is comparable to the speed of an airplane, and that guy cannot hit at so high speed. So for a golf ball, we usually make the surface rough so that the transition occurs at a lower Reynolds number. And if we replace this Reynolds number by 5 times 10 to the power 4, we only need less than 20 meters per second for a golf ball. So let's look at examples. In this chapter, the calculation examples are really easy. And there are 2 examples in the lecture notes, one about how to use the drag coefficient, and one about Stokes flow. And we look at 2 more examples. So we want to find the ratio of drag force. And since the velocity of these 2 conditions are the same, the drag force is only proportional to the drag coefficient. And the drag coefficient is proportional to the 1 over square root of Reynolds number. And the Reynolds number for a flat plate is proportional to the length. So this is just proportional to this guy. And in case B, the length is 4 times longer, so that the drag force is the drag force on the plate in case B is smaller than in case A, even though their areas are the same. So we shall look at an interesting example. The problem involves a composite body that involves the flagpole and the flag itself. Each have a drag force at its CG. This is the pivot at the base, and we label the given numbers. And we first calculate the drag force on the flag. And for the cylinder, we model it as an infinite cylinder, and we calculate the Reynolds number first. And we go to the previous graph for cylinder, and we are around here. We go horizontally. It reads about 1.2. So the area is the frontal area, and it is given by dl. The moment arm for the drag force 1 is half of the flagpole, and the moment arm for the drag force 2 is this length, and this is 20 minus half of the flag. So we find the overall moment. And we are done with this example. In this video, we talk about the definitions of drag and lift, and how to use the drag coefficient. We also talk about some physics about drag. First, we look at the effect of the Reynolds number. In particular, we look at flow over a sphere. We start from the Stokes flow and talk about flow separation, and end at a laminar to turbulent boundary layer transition. And then I give some remarks about the effect of geometry, and then we discuss the effect of surface roughness by looking at the golf ball example. So, thanks for watching, and so feel free to ask us any questions and give us any feedback in the comments.